Thank you. Everybody hear me all right? Probably. Everybody in the back. Great. So I'm really happy to be here. I've been in Flagstaff now for, I guess, a little over 3 years, and I've attended several of these seminars. Always enjoyed them, and it's a real pleasure to be able to be a part of this. Like many of us, I suspect, climate change provides a lot of the motivation and the primary impetus, and increasingly so, for some of my research. And while there are a lot of sources of uncertainty with respect to climate change, one of the things that's becoming increasingly clear is that we're putting a lot of CO2 into the atmosphere, and it's going to have an influence on climate. So these black dots are the global CO2 emissions, actual observations, and then the lines are what the latest IPCC forecasts, climate forecast models are based on. And the point is, we're still, if anything, we're a little bit probably above the highest forecast of the latest CMIP5 projections. And if these kind of trends continue along this red line, we're looking at something like maybe 5 degrees C increases in global temperatures by the end of the 21st century. It's really hard, I think, to overstate the magnitude and severity of the kind of impacts that this might have on ecosystems and natural resources, everything from changing species composition, altered productivity and ecosystem function. And so the challenges for land managers are really, I think, quite clear, and most of the land managers that I interact with are quite aware of these, increasingly so, but they're also sort of perplexed, and I think justifiably so, about what to do. And so the solutions are limited. They end up being these suggestions that are pretty vague, things like, well, manage for uncertainty, recognize that we know it's going to be different, but we don't really know how, and maybe try to develop strategies that hedge your bets against alternative future scenarios. Those are useful, perhaps, but not particularly actionable. So it's trying to get beyond those kind of vague suggestions that motivate some of my work and that drives some of the topics I'm going to talk about today. So there are really just 2 topics I want to talk about today. The first is stand density impacts on tree growth vulnerability to drought. The second is drivers of tree mortality in the West, and looking at specifically what role stand density might play in influencing tree mortality. And then at the end, I'm just going to touch on sort of an aspirational interest in trying to understand tree regeneration patterns as well. So for the first topic, trying to think about stand density influences on growth vulnerability, for this experiment, myself and a number of collaborators are using these long-term growing stock level experiments. If you're not familiar with them, they're basically experiments in which they're typically run by the Forest Service, but not always. Different density levels are applied to a stand, usually, despite the fact that these are several decades old. Usually the treatments were randomized, and they're typically replicated. They often have a control. So there are these really great experimental frameworks that a lot of folks several decades ago had the foresight to set up. They were originally designed for growth and yield, looking at timber objectives, but because they represent an obvious gradient in competitive intensity, they're also really useful for assessing how climate change and climate extremes might influence forest ecosystems and what role we could play to moderate those influences, perhaps by minimizing competition. And of course, we're not by any means the first or the only ones to think about this. In fact, some of the best work in terms of individual tree physiology for this is some work that Nate McDowell did when he was here several years ago, looking at the Taylor Woods growing stock level, which I'll talk more about later in the talk. He did a great individual tree assessment of a lot of physiological processes. I know Tom was involved in this as well as others. So we're not the first to think about this, but our goal is to really try to apply these ideas over long time periods and over as many sites as we can find across the country, and potentially expanding even further. So our main goal here is to try to understand how does basal area density influence stand level response to environmental extremes. And we started out thinking pretty broadly about environmental extremes because this work started when I was in Minnesota, northern Minnesota, where it's quite cold and water limitation is not on very many people's minds up there. But even in those systems, and in fact even in systems in the Northeast, we're now really focusing on drought as the primary driver of fluctuations that we're trying to moderate with these stand density treatments. So it's kind of interesting that we've really evolved to a focus on drought even across a wide climatic gradient. So our approach here is we establish measurement plots in the different basal area density treatments, collect increment cores from all the trees greater than a threshold, typically 10 centimeters diameter. So that's one of the differences between what we're doing and some of what's gone on before, is that we're capturing measurements from all the trees on plots so we can try to assess and evaluate stand level growth patterns. Of course, cross-date the chronologies, convert to basal area increment, and then examine growth response to specific drought events. So we try to focus on years of known droughts at each site. We try to look at a pre-treatment drought to make sure there aren't existing differences among the stands, despite the fact that the treatments were imposed randomly. And then we look at an early drought shortly after the experiment was started to assess sort of the short-term impacts of the treatment. And we typically look at a long-term drought at least a few decades after the treatments have been imposed. So this gives you a feel for kind of what the data look like. The top panel here is tree-level basal area increment. And this is 4 different levels of growing stock. This happens to be the Taylor Woods experiment right here outside of town. See, the trees are all growing pretty similarly, and then the experiment is implemented. These trees are thinned down to a much lower density than are these other trees. You can see the trees where the densities are low have a much higher growth rates. This is tree level. When you sum it up to the stand level, of course, the results are somewhat inverted. Now we have our lowest density at the stand level displaying typically the lowest growth patterns, and the highest level having the highest growth patterns. And it's these kind of results that we work with in terms of assessing stand level drought response. So the specific response variables that we're looking at for each given drought event we're looking at 2 of them that I'll present today. The first one is resistance. So this is the ability of the stand to avoid growth reductions during the drought event itself. So it's the basal area increment during the drought divided by the increment before the drought. So how much did growth go down while the stand was experiencing drought? The second metric is what we're calling resilience. It's the ability to regain the pre-drought growth after the drought ends. And it's typically done in a 5-year window. So what was the average growth in the 5 years after the drought compared to the average growth in the 5 years before the drought? So the first place where we tried to look at this was actually a red pine plantation in northern Minnesota. This is when I first started thinking about these questions. It was 45 years old when the treatments began. We examined 5 basal area treatments as well as controls, replicated 3 times, and thinned several times after it was initiated in 1957. And these are some results from a paper that came out of that work a few years ago. The top panel, well, the left column is all resistance. So again, this is how much is growth declined, or how much ability does the stand have to maintain its growth during the drought. The left column is resilience. How much does the stand regain its growth after the drought is over? The top 2 are results for a drought that occurred before the treatments were imposed. The middle is a drought shortly after the treatments were imposed, and the bottom is a drought that occurred about 3 decades after the treatments were imposed, so kind of a long-term perspective. The different basal area densities are on the x-axis, from low density on the left to the highest density on the right. No differences before the treatments were imposed. That's nice. In the short-term drought, or the early drought, we see clearly that the lowest density stands have the highest resistance and the highest resilience, and generally declines with density. However, when we looked at the drought that occurred after a few decades, the highest levels of resistance and resilience were actually at intermediate levels of stand density, and we weren't and really still aren't sure if that's because perhaps the trees in the low density, by now they were almost 100 years old, not that particularly old for red pine, but they also were quite a bit taller than some of the trees in the other stands, and so there may be physiological constraints. It may be an age effect. We don't know, and still don't have a good handle on that now. Our next step was then to try to expand this to a much broader number of sites, and so we've now brought in 8 different long-term experimental sites. My collaborators in this larger project, and Tony D'Amato, Sean Fravor, and Brian Palak have been involved in this from the very beginning. Tony was at the University of Minnesota. He's now with Vermont. Sean Fravor is now at the University of Maine, and Brian Palak's with the Forest Service in Minnesota. We also have collaborators, including Alexander Botero, who's a postdoc working with us. Mike Battaglia is with the Forest Service, as is John Brissett, Todd Hutchinson's Lewis Iverson, and Laura Kennefic. So mostly a bunch of Forest Service folks from across all these different locations. We have 2 sites in the Northeast, a conifer and a hardwood site, 1 oak site in Ohio, 3 sites from the lake states, including the Birch Lake, which I just showed you some results for. Argonne is a northern hardwoods. And then we have 3 sites, the Cutfoot, the Black Hills, and of course Taylor Woods down here that you're all probably familiar with, that represent a climatic gradient from quite arid up to colder and wetter. And it's those 3 sites I'm going to tell you a little bit more about, some of the preliminary results expanding on the Birch Lake study for those. So again, the 3 sites, we've got in the north Cutfoot, it's also red pine, it's over 70 years, the experiment's been going. You can see the precipitation and temperature. Generally, as we move from Cutfoot to Black Hills to Taylor Wood, precipitation goes down and temperature goes up. So clearly an increasing aridity gradient from northern Minnesota down here to Arizona. So when we are trying to merge these experiments together, rather than using a categorical representation of stand density based on the treatments that were imposed, we wanted to find a way to have a continuous variable that would allow for the reality that even though a certain basal area density is what's supposedly implied, of course that varies through time, it grows after the thinning, so I wanted to actually incorporate the continuous measure of density when the drought actually occurred. And we wanted to have some way to try to standardize across these 3 different locations. So to do that, we're using relative density. It's just calculated as the current stand density index divided by a metric of the potential maximum stand density index. Provides a measure of overall density that's independent of a given site. So these are some of the results from these 3 sites. Again, I have resistance on the left, which is the extent to which the stand sustains its growth during the drought. Resilience on the right, which is the extent to which a stand regains its growth after the drought. Again, low density, in this case it's relative density on the left, high density on the right for all the plots. The 3 different colors, black is for the Black Hills, the reddish color is for Cutfoot, and the green is for Fort Valley. A couple of main take-home points to take from this is for all these experiments, for all 3 of them, and for both the early drought and the late drought, they all show negative relationships, which suggests that stands with lower densities are more resistant and resilient. And this was a little bit surprising because the Birch Lake had this shifting relationship in the older, or at least later drought. And we don't see any evidence of that in these 3 sites. So we're still not really sure what happened, what's going on with Birch Lake. But all of them show decreases, which do suggest that there's some, at least across this climatic gradient, consistent potential for mitigating drought effects on stands by decreasing stand density. One of the nice things about having sites that represent this broad climatic gradient is the potential to look at how overarching climate might influence the relationships between drought severity, perhaps, and either resistance and resilience. We looked at that. We also looked at the most important drought metric and found that there's quite a bit of difference. So the 2 northern sites, Cutfoot and Black Hills, the best drought metric for explaining resistance or resilience when we look at drought severity versus resistance and resilience using all the treatments together was the standardized precipitation evaporation index, whereas here at Taylor Woods it was the forest drought severity index developed by Williams and others a couple years ago. So perhaps not surprisingly, this metric, which is developed for the Southwest, does in fact perform best for trees in the Southwest. There's also at least some evidence. We're right now in the thick of trying to explore this more completely. There's some evidence that this relationship between ecosystem response and drought severity might be tighter and stronger in the sites that are in increasingly arid situations. So the strongest relationship is here at Fort Valley, and I'm really curious to try to untangle the effects of the stand density from drought severity and see if, in fact, there is more reason to think that there'll be more sensitivity to drought in the warmer, drier places like down here. So our next step here, one of them is we're planning to use an ecosystem water balance model to enhance our representation of drought. So from some of my other research and other avenues, I do a lot of water balance modeling, and want to use that same model in these same sites and try to get metrics of drought severity that include daily metrics of available water throughout the growing season, so we can see if those enhance our ability to understand stand responses. We're also interested in refining our relationship between drought severity and the resistance and resilience across densities. And if anyone is interested, I have a current postdoc opportunity right now. It's on USA Jobs to do some water balance modeling and assessments in these set of sites, including the full 8 that we've got going right now. So keep that in mind. We also have a technician position for other soil water balance modeling that's maybe a master's level position. So lots of opportunities. Let me know if you're interested. And then lastly, I want to try to assess sort of what are the applicability of these stand density insights two sites that are not part of experimental forests, that are just the way forests exist when they're not managed, which of course is most of the forests out there, especially in the West. And that kind of leads into the second topic, which is looking at tree mortality in the West and trying to assess what role stand density might play in moderating that. So this is a paper that came out just a few weeks ago in Science Advances that looked at forecasts of drought severity and how that compares to the last 1,000 years for the Southwest, and it suggests we're likely to move into an area of unprecedented drought severity, and this metric is soil moisture. I kind of cut that off there because I cut off the different region, but this really suggests that from a climatological point of view, we're moving into territory that's going to be really interesting for forests. And then most of you are familiar with this work, the Park Williams and others, in which they developed the Forest Drought Severity Index I mentioned earlier. It's based on warm season VPD and temperature and cool season precipitation. When you take that metric and look out in the future, and this was a metric that's been closely related to the tree responses, it goes quite into the negative territory. So further evidence that even for trees specifically, we're going to have some real challenges in the next several decades. And then this paper's become quite famous, looking specifically at drought-mediated mortality. Craig Allen and others, there's a lot of sites in North America included in this, and he suggested this paradigm in which you have species existing in a current climate, and then what happens when that climate moves into a future conditions where the mortality threshold is crossed at a higher proportion of sites and times, and you start to see increasing mortality. So some of these kind of ideas that motivated my interest to look at drought mortality in the West and specifically see what could potentially be done to mitigate that using density reduction. Excuse me. So my collaborators here, well, overall question is quantify tree mortality response to climate, weather, and stand density. The collaborators are Dave Bell, who's now with the Forest Service Pacific Northwest Research Station. Dave gave a seminar here, I think, last year, maybe. And many of you probably know him. He was here for his master's degree with Margaret. And Bill Auenroth at the University of Wyoming. We have pulled together FIA data for plots that have repeat measurements. So plots where they measured it in the same way in the 1990s, and they measured the same plot in the same way in the 2000s. They've been changing their protocol a lot, but this was some of the first times they were repeat measurements. They don't specifically link up trees, but you can link trees if you look at where they are located on the plot and check the species and check the size, make sure it all makes sense. So we had to write some algorithms to go through and do all that with all these trees. So we have about 120,000 trees that we've confirmed are the same tree from one measurement to the next. And that's what we're using for this analysis. I'm just focusing here on 6 species: subalpine fir, Engelmann spruce, lodgepole pine, Douglas fir, ponderosa pine, and two-needle pinyon. This kind of shows you how those species fall out in the climate space. At least these are the climate space occupied by the plots in this data set that I'm working with. So you've got the higher elevation subalpine fir and Engelmann spruce, grading over to warmer and drier as you get down to pinyon pine. So this is just a snapshot of sort of what the data looks like with respect to total number of trees and mortality rates. Species are ranged here from high elevation, subalpine fir, Engelmann spruce, lodgepole pine, Douglas fir, ponderosa pine, and pinyon pine. The total height of the colored bar is the total number of trees. That relates to the left axis. And the black are those that died, and the green are those that survived. And then the red unfilled bar is the annual estimate of mortality rate, and that relates to the right axis. So you can see it goes from about 1% here to about 3% per year up here. And it does look like perhaps the lower elevation species are having higher mortality rates over this period. So there were 4 questions we wanted to try to answer with this data. The first is what climate and weather variables are most related to tree mortality over this interval. So for climate, I mean sort of the long-term climatic conditions that characterize a given plot. So I use PRISM's 30-year normals for this. Excuse me. For weather, I mean the maximum or minimum conditions for any season or year that were observed in between measurements. So they went out and they measured a plot in some year. They knew the tree was alive then, came back later, it's alive or dead. In whatever years those were, what was the maximum or minimum values for temperature or precipitation that occurred over that interval. So it's a metric of climate seasonality or weather, climate extremes or weather extremes. And then once we've identified which climate or weather variables are most related to mortality, let's look at what climate change suggests for the future trajectories of those variables is likely to be over the next 100 years. So to do this, I'm using 10 global climate models. These were identified from the large set of climate models in the latest CMIP-5 modeling effort as most accurate for the western United States. So Rupp and others did a hindcasting assessment where they compared all the models' assessments of what the climate should have been over the last 100 years or so with what was actually observed and identified those that worked best for the western United States. And then we also selected those that represent a range of GCM structure, which is something not often recognized. You can't just take all the climate models because some of them are essentially the same model with some small different tweak. So you get a very biased representation if you just take them all. We looked we extracted the values for each plot from these models for a 30-year period in the middle of the 21st century and a 30-year period at the end of the 21st century to kind of provide a near-term and a long-term assessment of what climate change might mean. The third question is relating it back to our initial topic about stand density. How does stand structure, especially basal area, influence mortality? Is there evidence that it matters in these species? And then the fourth question, sort of bringing together all three of the ones before it, do we have some evidence that density reduction can be useful at mitigating mortality driven by climate or weather? And in particular, can it be useful in the conditions where we're experiencing high mortality now and where we expect to in the future? So the approach here that we've been taking so far is a Poisson regression. I've tried zero inflated models. I've tried negative binomials. I'm still not satisfied with the way it's working, and Dave Bell and I are still working on finalizing how we're going to do this. But the bottom line is no matter which approach I took, the general story didn't change much. So I don't think it's going to change the story. We may refine the methods a little bit. Show you what that looks like. This is ponderosa pine mortality rate. This is on a log axis as a function of mean fall temperature. So that's climate temperature. You can see an increasing mortality. This just suggests that places that are warmer for ponderosa pine are experiencing higher mortality rates. Take that and put it on a linear axis, and you have a curve like this. And this distribution, if you can see that, I don't know if it comes up better for you than me, that's the distribution of all the plots in that climate space. So to give you a feel for where the plots actually exist relative to this climate driver. So this rate goes up pretty high here, but there's almost no plots out there. So that's just a construct of the model fit. So we did these. Oh yeah, so the question we're looking at here is what climate and weather variables are most related to tree mortality? We did these regressions for predicting mortality from the best temperature variable for annual or seasonal mean. So this is 5 potential variables. Chose the best one. 5 potential precipitation variables. And then for weather, we took the best interval measure of temperature or precipitation. So this is 10 variables it's choosing from, maximum or minimum, for each annual or seasonal metric, to try to boil down this soup of results into something that's relatively intelligible. So what I'll show you are sort of the 2 best climate predictors and then the 2 best weather predictors for each of the species. So let's start with the climate temperature predictors. And this is one of the 2 pretty clear and consistent results that came out of this climate and weather analysis, and that is that we see positive relationships between a metric of long-term temperature on the x-axis and mortality rate for all the species. So a number of these plots are these plot layouts I'll be showing. We start with the highest elevation species here. I move down all the way down here to the lowest elevation of those 6. So all 6 of them really suggest that mortality is highest where it's warmest within the range of that species. It's true that the specific metric of the seasonal metric varies some. So for these 2 species, it's fall. For these, it's winter. But it's important to note that for temperature, there's a high correlation between seasonal metrics of temperature, especially with respect to climate. That's not necessarily true for precipitation, but it is very true for temperature. So clear evidence that mortality is highest in places where it's warm. Looking at the climate precipitation impacts for 3 of the species, subalpine fir and Engelmann spruce, as well as pinyon pine, we see increases in mortality with increasing mean summer precipitation. So mortality was highest where the summers are wet for these species. It makes some intuitive sense up here, perhaps, shorter growing seasons. This is, subalpine, pretty high elevation species. I'm not sure what to make of that for pinyon. For the other three species, lodgepole pine, Douglas fir, and ponderosa pine, mortality was highest where summer or spring is dry. So we see negative relationships with spring precipitation and the highest mortality in places where it's dry, and summer precipitation for lodgepole. So looking at weather extremes or climate extremes, for the subalpine species, we see that mortality was highest where the coldest year was very cold. So these are negative relationships with winter, fall, or spring temperatures. Saying the highest mortality occurs in those locations that experience an extremely cold year, and the season varies a little bit. Whereas when you look at the lower elevation montane species, this is really flipped, and it's a different relationship. We see that for Douglas fir and ponderosa, increasing relationships with fall temperature. So mortality was highest where the warmest fall was very warm. And then for pinyon pine, suggests that mortality was highest where the coldest winter was not cold. So maybe this is a insect-related phenomenon. I'm not sure. I'd welcome your thoughts on it. It's a little bit, from a pure climate physiology, it doesn't seem to make a lot of sense to me, but maybe it's an insect-mediated response, where if you didn't get a cold winter over that interval, you have higher mortality. All right, so weather precipitation, this is the second of the really clear results with respect to climate and weather, and that is that mortality was highest where the driest winter was very dry for all these species, including the two high elevation species and the three sort of montane woodland species. For lodgepole pine down here, it's a little bit modified. Mortality was highest where the wettest winter was not wet. And it's as good a time as any to make the point about, well, I'll make that point in a minute. So, the next thing was, all right, we've identified some of the important, or at least strongly related drivers of tree mortality in this data set. What does climate change suggest the future of those drivers is going to be? So to do that, I build a model that's a multiple regression based on the best precipitation variable, the best temperature variable. So this is ponderosa pine. We've looked at both of these. Spring precipitation and fall temperature are the climate variables that are most influential. And then show in the climate space that species exists. In this case, the color relates to mortality rate, with green being low mortality and red being high predicted mortality. So you can see in the areas where ponderosa pine exists, generally you have higher mortality as you move to the right in this case, which is moving to higher temperatures. So it really underscores the role that temperature plays for ponderosa pine. While spring precipitation was significant, as was the interaction, it doesn't show up very clearly, at least on this plot. So we'll look at these results, well, before we look at all the species. What we then do is say, okay, now we know a little bit about what the mortality looks like relative to these drivers. Let's look at what the future holds. So in this case, I've colored the contour lines to show you the distribution of plots within the current plot locations. And then I've done the same contour lines, just without showing the individual plots, for a mid-century, which is in purple, and an end-of-the-century climate space. So this essentially says where in climate space are these same plots that have ponderosa pine now likely to be in 50 and 100 years. And you can see for ponderosa pine, here's where they exist now, and they're clearly moving into this, moving to the right, which means warmer, and a little bit up, which means a little bit wetter, also spreading out a little bit more on the precipitation axis. But since there's a clear increase in mortality with increasing temperature, this is not an optimistic picture for the future of ponderosa pine, since we're moving into these increasingly warm conditions. So we can look at the future forecasts for all the species. For the subalpine species, you can see that the future forecasts are really dominated by these increases in precipitation for all three of them. I mean, these distributions in the future are quite elevated on the y-axis. And I checked the extractions. I'm a little bit surprised. This is not really what I expected the climate forecast for these high elevation locations is, but if anybody's a climatologist and can speak to this, I'd love to hear it. Maybe it's reasonable. As temperatures go up, there's a reasonable think there's going to be more moisture in the air, and maybe these mountaintops are really going to do a a good job of extracting that moisture? I don't know. But given that situation of increasing forecasts for precipitation, for some of the species at least, it looks like those precipitation increases may ameliorate some of the mortality risk. I mean, obviously there's increases with temperature here for these two species, but adding that much more precipitation may help moderate that. For lodgepole, it's pretty clear that wetter conditions are where mortality is lowest. For the lower elevation species, it's again sort of a different story. So for Douglas fir, ponderosa, and pinyon, all three of them show more pronounced shifts to the right, meaning increasing temperatures, than they do show increasing precipitations. And all three of them, like if you look at the colors, show increasing mortality very clearly as you move to the right. So it suggests the potential for relatively consistent increases in mortality risk for these three low elevation species. Okay, so the third question is to look at how stand structure, in particular stand basal area, influences mortality and see what potential there might be for mitigating some of these risks. So to do that, in this case, I wanted to step away from plot level relationships and look at individual tree level. So I did a logistic regressions on individual trees with tree diameter or plot basal area as the independent variable. Some of those plots are shown here. So this is probability of mortality. This is tree diameter. This green distribution is the distribution of trees that survived. And this, whatever color that is, fuchsia, is the distribution of trees that died. And then the relationship is shown here. So for ponderosa pine, the data suggests that larger trees are less likely to die in this data set. And trees in higher densities are more likely to die. So this probably comes as no surprise to anyone here that having ponderosa be big trees by themselves is a good situation for them. All right, let's look at the size relationships for all the species. So for the subalpine species, all of them show positive relationships, which means that larger trees are more likely to die for all three of those high elevation species. For the low elevation species, actually, pinyon and Douglas fir show no relationship between tree size and mortality, but lodgepole pine shows the decreasing trend we saw before. For stand structure, this is another very consistent result. For all 6 species, trees in dense stands are more likely to die than trees in less dense stands. So in some ways, maybe this is encouraging. It suggests there may be some potential for, if we can through management shift stands to lower density, maybe we can ameliorate some of the mortality risk. And that's the question that I really wanted to try to address with this fourth and last question. So can density reduction mitigate mortality in vulnerable locations? To do this, I built multiple regressions of mortality as a function of precipitation, temperature, again, those same variables that were identified as the best. They had the highest fit within each of the categories, and plot basal area. And then I quantified the range of mortality between low and high basal area conditions, and also quantified it at median basal area. And then I calculated an index of basal area impact as the mortality at low density minus the mortality at high divided by the median. So one way to interpret this is what proportion or percentage of expected median level mortality might be able to be reduced by modifying stand density. And I show all these plots on the same axis from 0% in black to 100% in yellow. So again, ponderosa pine, here's what your mortality looks like. It might be at low basal area. Here's high basal area. Doesn't look like there's a whole lot of difference, although if you squint, you can kind of see there's maybe a little more green here, a little less red. Take the difference and divide by the median, which is in between those, and see where density reduction might have the potential to make a difference. And for ponderosa pine, the largest difference is in cool and dry conditions. But the impact is not as great as some other species. It's only maybe about 35 or 40% total. So then it's useful to kind of contrast this assessment of where we may be able to be effective with density reduction with, again, where mortality is high and where we're moving in climate space. So for ponderosa pine, we're most effective down here, as you can see looking from this, but our mortality is really highest over here, and we're in fact moving up and to the right to wetter and warmer conditions. So it underscores some of the challenge for mitigating ponderosa pine mortality, at least with density reduction. So we can look at this for all 6 species. We'll start with just the 3 high elevation species. For subalpine fir, we see that mortality mitigation or density reduction is most effective in conditions that are cool, which is consistent with where we are headed in the future. So there's some suggestions that it may be effective for climate change mitigation. For Engelmann spruce, it's most effective in conditions that are cold and dry, which is not where we're heading, so it's not likely to be particularly useful for mitigating climate change impacts there. For lodgepole pine, it's most effective when temperatures are warm, which suggests there's at least some potential. So a lot of the high mortality areas are over where temperatures are warm, although it's mostly driven by precipitation for lodgepole. The low elevation species, especially Douglas fir and lodgepole pine, have sort of a pessimistic Douglas fir and ponderosa pine have kind of a pessimistic message. The most effective mortality mitigation through density reduction is in conditions when it's cool and dry, which is exactly not where the climate forecasts are pushing us. And then a little bit surprising to me, at least, the pinyon suggests that mortality mitigation is actually quite effective over a pretty large area, and especially where winter temperatures are high, which is right in line with where the mortality is highest and reasonably consistent with where climate change is pushing us. So, I don't know. I'm interested to hear your thoughts on if that makes sense. So I have the same plots for weather and the ability of density reduction to mitigate weather effects, but I think I'm going to skip over them. They're really pretty consistent with the climate effects. So this is a lot of different sort of isolated results, a lot to try to ingest and understand. In an attempt to try to bring this together and provide a big picture assessment of what this says about tree mortality in these 6 species, I kind of return to this climate space and think about these 6 species arrayed across this climate gradient. And I used hierarchical partitioning to identify the independent effect of these different variables on overall mortality rates. This was done on an individual tree basis. So we've got plot basal area in green, tree size in brown, and then the 2 weather variables, temperature and precipitation over the interval. Those are in the darker colors. And then the best climate variables, temperature and precipitation with respect to long-term means. And you can, what's showing here is the proportion of mortality variability that's explained by those different categories in species ranging from subalpine fir all the way over to the low elevation species. So this allows us to kind of recognize where different drivers are important and does suggest at least some different ways to conceptualize what's driving mortality in these trees. So for high elevation, subalpine fir, Engelmann spruce, and lodgepole pine, structure, the green and the brown, is quite important. As much as maybe 50% of mortality is seem to be explained by structure. And a lot of that is this brown tree size effects. And if you remember, these were all positive effects. So for these trees, large trees are more likely to die, and that explains a lot of what goes on with tree death in these high elevation species. To the extent that that climate and weather are important, climate is less important than weather, so weather has a bigger influence than does climate. In particular, extremely dry winters and extremely cold conditions are the primary drivers. So these red bars are both decreases in mortality with increasing minimum temperatures, and then decreasing mortality with increasing winter precipitation. Useful to note also that these drivers are not what we're expecting with the climate change. So these are probably pretty resilient to climate change because we're not going to see drier winters, and we're not likely to see colder conditions. And those are the drivers of mortality for these high elevation species. For Douglas fir, which is in the middle, stand structure has the smallest role of any of the species. And really this red bar, which is the influence of weather temperatures, so extreme temperature conditions, is the primary driver. And if you recall, that was a positive relationship with maximum fall temperatures. So as fall temperatures get warmer, this may increase, and this, of course, that's one of the projections of climate change. So this species does appear to be pretty vulnerable to climate change. The two low elevation species, lodgepole and pinyon pine, have sort of intermediate levels of stand structure importance, but of that importance, it's mostly stand basal area and less so tree size. And the results that we showed earlier suggest that density reduction may be more useful for pinyon than for lodgepole. Of the climate effects, in both cases, these big pink bars are positive relationships with fall temperatures. So again, as fall temperatures go up, mortality may go up, and this does suggest some vulnerability to changing climate. So this climatic gradient, I think, is kind of useful for trying to understand the big picture of what we see here. In fact, just Monday, I think I came across this recent article on PNAS. Some scientists from Canada did a somewhat similar analysis, and they looked at mortality, regeneration, and growth rates. And their title says it all, that the dynamics, and this was especially true for mortality, are really driven more by competition, metrics related to stand structure, than they are to climate. So if you imagine continuing this climatic gradient to colder and perhaps somewhat wetter conditions like they might have in Canada, and the role of stand structure becoming more important, that's consistent with what they found. Dave Bell and I did a paper a couple years ago on aspen, and suggested that the climate played a very large role in aspen mortality as well in the region. So aspen's probably right around in here somewhere in its climate space. So that's also relatively consistent with some of these results of a gradient in importance in stand structure, and perhaps a gradient in importance in stand structure, and also a potential gradient in importance in climate versus weather. All right, so the next steps for some of this work is I'd like to try to consider some alternative metrics of weather. So, if these are all isohydric species, I'm not certain they are, but if they were, it might be reasonable to think that perhaps the kind of drought that's going to be a problem for them is not an individual severe season, which is the finest temporal resolution I have here, but perhaps it's a 3-year period of sustained stress that would cause a carbon starvation-driven mortality rather than a punctuated mortality. So maybe we should be thinking about different ways to conceptualize the important driving variables. I'd also like to expand to some other species, in particular juniper. So I had juniper in all these results and have all the data for it, but I didn't present it here, and I probably won't include it in at least some of the early publications because it's just so completely different. Its relationships are completely different with a lot of the drivers, and the mortality rates are a small fraction of what the mortality rates in any of these species were. So it seems to be a very different process going on with juniper, but it could be really interesting to explore and contrast some of the drivers we see here with those that exist in juniper. If possible, I'm interested in trying to find a way to relate the mortality of these species to the more detailed metrics of soil moisture using the same kind of modeling I mentioned earlier. And I'd like to start thinking about the climatic drivers and potential climate change projections for other processes as well, like growth and mortality. Or excuse me, growth and regeneration is what that should say. Which kind of leads to my last thing I want to just sort of mention an interest in, which is tree regeneration. I think it's reasonable to think that tree regeneration may be as important for the future of forest sustainability in the West and the Southwest as is mortality. So mortality has received a ton of attention over the last several years, but if you think about perhaps if mortality rates go up but regeneration remains constant, you may just drive down the age structure of your population of trees. Whereas if you start undermining regeneration and you have regeneration failures at an increasing frequency, you may undermine overall sustainability of forests as a whole. So I'm really kind of excited to think about taking some of these same perspectives on tree regeneration. Some of what sort of started with that is I'm trying to work through a literature review / meta-analysis, if possible, looking at the environmental controls over regeneration for lodgepole and ponderosa. So what do we know about soil temperature, soil moisture drivers of regeneration? I'd like to try to relate that to stand structure and try to think about modeling the episodic nature of regeneration under current conditions and also future conditions. So if we go from a long-term average of 1 in 50 years are really good for regeneration to one in 250 or one in 500, that could have a big influence on forest sustainability. So some of the folks I'm really just kind of talking to about this and working with a little bit, Tom Kolb, Keith Mosier, Kristen Waring, I think Kristen's in here somewhere. And Kelsey's working on some of these questions for her master's degree at Taylor Woods. So I'm really excited to see how some of those results come out and start thinking about folding those insights into the soil moisture modeling and long-term climate change projections. So just to sum up, I think I've still got enough time. Looking at these existing long-term experiments really does suggest that some of the forest management strategies that have been utilized and recognized and studied for decades, if not centuries, by silviculturists and forest ecologists can be really useful, I think, for understanding possible strategies to deal with climate change. In particular, density reduction may be useful for mitigating drought impacts on forests. Looking at the application of that idea to tree mortality, we really find that in the West, at least, in this data set, mortality is highest in places that are warm, and that's defined by each species range, and it's highest when winters are especially dry. And so climate change may really increase mortality for some of the low elevation species, but it's not as clear if it's going to have an impact on the high elevation species. And density reduction, it may be able to mitigate some of that mortality, or that expected mortality, for some of the species and in some locations, but certainly doesn't look like it's going to be a silver bullet that works everywhere. It's going to be something that may be most useful in certain times and certain places, and so it'll have to be applied and utilized very carefully. And with that, thank you. Yeah. Well, the results don't suggest that large trees are more vulnerable to drought mortality, just that large trees are more likely to die. So mortality rates are higher for large trees. That doesn't mean that it's drought that's driving those large trees over the edge to mortality. So I'm not sure that I would have a mechanism for that, because I'm not sure that's necessarily what's happening. So we have one relationship where bigger trees are dying at a higher rate, others where droughts, when conditions are bad, more trees are dying. Yeah, I don't have a good explanation for that. Some folks in here might have better ideas than I do. It was pretty clear across all three of the species that relationship exists, but perhaps there's, in the truly high elevation species, the Engelmann spruce and subalpine fir, some of the ones up near tree line, there may be extreme cold effects, especially with wind, and being taller may be detrimental. I don't know. I don't have a good explanation for it. One of the things I should have said in here that really applies mostly to lodgepole is that the dates in which these measurements were taken do include that pretty dramatic bark beetle epidemic. And I looked at the data and tried to filter where they gave us codes for what caused the mortality, but only about less than 0.5% of any of the mortality events have a code assigned to them. So taking those out didn't change any facts. So it may be that in a species like lodgepole, larger trees may be more influenced by the beetle epidemics and beetle mortality. And that may be the case as well in spruce and fir, but I don't think that their widespread mortalities would be in some of this data, because the last collection for this, I think, was about 2005, but that's one possibility. Yeah. Well, so this is FIA data, so I haven't tried to construct stem maps and assess where each stem is relative to an opening. I've tried a couple other metrics, and the other one I was really optimistic about but didn't work out was the proportion of basal area that's bigger than the tree. So the proportion of trees that are larger expressed as proportional basal area, and that wasn't very influential. So I've looked a little bit, but didn't find significant relationships, or at least very many, for that variable. I'm not sure how I'd get at patchiness or closeness to patch. It's possible, but not with the data as it's currently structured. Yeah, Tom.
John, related to the mortality work that you're doing, which I think is really interesting, it wasn't clear to me whether you included sites that had burned. So are fire effects included as a possible mortality agent there?
So they are included in this, and they make up about 0.45% of trees that have an agent assigned. About 0.25% of that, or 0.25%, so more than half, is fire. So we have that information about some. They're included in these figures. When I took them out, it didn't change the results any because it's only 0.25% of all the data. So I have a hard time believing that it isn't more prevalent in the data set, that more of these trees that die are a result of fire, but I have no way beyond those codes to know which ones. So I tried, and it tried to remove them. But I'm not, I can't speak to why those codes aren't more prevalent in the data set. But by code, I mean there's an agent code category there. They say if it died, they can provide information about why. And
I wonder in the FIA data collection, would there be some bias about not remeasuring a site that has 100% fire, or are they routinely remeasured?
I think they're supposed to be routinely remeasured no matter what. So other folks may know more about FIA in here, but I think that's the idea, is they do them. Do you think, is that right, Andy? Is that what your impression? So maybe there's another place to find it?
Yeah.
Well, maybe I should look at that.
It's a table structure at the subcon level.
Yeah. Well, I have that data. I haven't looked at that, though. Yeah, it's a good question. One I've thought about, too. I was hopeful there'd be more information in those codes, and I could extract and tease out the either fire or insect-related mortality. Yeah, Matt. I'd have to look back at what the specific drivers were on those high elevation species, you mean? So these two are both spring precipitation, and this one's summer. Yeah, and I mean, we'd expect, the climate expectations for a warmer world are more average global precipitation. So I'm not sure, but that doesn't mean very much at any given location. I was kind of surprised at the extent to which increasing precipitation seems to be a feature of essentially all 6 of the species ranges, especially the high elevation ones. And a lot of my research looks at sagebrush ecosystems, and we've had similar sort of surprises in looking at the climate forecasts for some of those sagebrush. A lot of them, especially the northern part of the sagebrush range, they really call for pretty remarkable increases in precipitation, and that there's a latitude line at which that sort of switches as you move south. So that optimistic story doesn't really apply down here, at least to the lower elevation species. But it's been a regular feature of looking at dryland forecasts for climate change. In fact, another project, we're doing some global assessments of temperate drylands, and most places have increases in precipitation forecast at some varying degree. So, yeah. Well, they're certainly less certain than temperature, because temperature is directly related to CO2. So these lines are the distribution of a climate model that was the median value for this particular driver. So of the 10 models I looked at, there's, it's the average of the 5th rank and the 6th rank model. So there should be 5 models that are lower on this metric and 5 models that are higher for this. So this is kind of the center of those 10. And I tried drawing the lines for all 10, and it was unintelligible. But yeah, I don't think it's a consequence of the ensemble, because all that is just taking the middle value of a set of however many, in this case 10. It does seem to be a pretty consistent thing that we find in a lot of places. Yeah, Pete.
Flip back to the map that showed where the everybody across the board.
No, that's all right. Sure, you guys want to relive this, right? Just what you need.
So they range all across from Mexico to Canada.
Yeah, well, this is the Wyoming border. Or this is Wyoming. Yeah, so Black Hills. So we have a few points, I should really say, when I say we, I say Dave Bell pulled all this together and did all the checking of the trees. It was not a trivial piece of work. But there were very sparse plots that had been repeatedly measured in Montana and Idaho, so I just cut those out for this analysis because they really expanded the climatic range without really expanding the sample size commensurate to it. So I clipped it off there. So that goes through Wyoming.
I was kind of thinking about that climatic range. It's a little bit related to Matt's question in a way that even the existing precipitation and temperature patterns can be really different within the same species, and especially from Ponderosa,
Yeah.
which is going from a continental to a continental climate. And
Yeah.
so like you have a fall temperature show up as an important variable.
Mm-hmm.
Fall temperature has to already be dramatically, I would think, different between here and the Black Hills. I don't know.
No, I think that's true, and I've thought about the potential for, maybe just focusing on Ponderosa and looking at because it represents such a wide gradient in climatic conditions. I mean, these Black Hills sites are mostly Ponderosa, and they're about as far from down here as you can get. Yeah, I had the same thoughts, but haven't tried to tease that out yet. One way that I've thought about maybe doing it is building a multiple regression model that has both climate and weather at the same time, which I haven't tried to do. So your influence of weather extremes would be allowed to depend on what your overarching climate is. It would allow places in the north where you have very different climatic conditions to have different extremes that matter than places in the south. Haven't tried wrestling with that. And multiple interactions within that become complicated quickly, but it's a very good point.
All right, well, if that's it for questions, we'll conclude the seminar. We have a discussion with the course in our class in room 34A from 5 to 6.
Thank you.